Electricity did not invent the computer. It did not make a machine intelligent, but it changed a basic question of modern life. How can power move, be transformed, and be coordinated across distance? In the late 19th century, engineers and businesses began to build systems that made energy available far beyond the mill, the mine, or the steam engine that produced it. Their work reorganized streets, factories, homes, and eventually the infrastructures on which electronic communication and computation would depend. This is not a story of one lone genius switching on the future. It is a story about systems. In 1876, Thomas Edison opened his laboratory at Menlo Park, New Jersey. It became one of the most influential early sites of industrial research and development. Its importance was not simply a list of patents. Edison brought machinists, chemists, glassworkers, draftsmen, and experimenters into one coordinated workspace. Invention became less like an isolated flash of genius and more like a process. Test a material, revise a design, build a prototype, record a result, try again. Menlo Park did not invent modern technology companies, but it made organized collaborative invention visible on a new scale. Edison's lighting achievement was also a system, not merely a bulb. By 1879, his team had developed a commercially successful incandescent lighting system, linking lamps to generators, wires, distribution equipment, meters, and maintenance. A lamp could glow only because an entire network of components worked together behind the wall and beneath the street. This mattered because electrification asked society to coordinate new kinds of labor, people to generate power, install cables, repair lines, read meters, and pay for service. The visible light was only the surface of a much larger arrangement. Edison's early direct current network was designed mainly for relatively short distances. Its low voltage distribution made sense in dense urban districts, but reaching farther meant building more local generating stations and more local infrastructure. That was not irrational. It was one competing architecture of the electrical city. Yet it raised a problem that would define the next phase of electrification. How could power be sent farther, then made safe and useful where people needed it? The answer did not belong to one person. It emerged from a wider system of transformers, generators, motors, firms, investors, skilled workers, and public decisions. Nikola Tesla became an important figure in that wider system. Born in the Habsburg Empire and later working in the United States, Tesla briefly worked for Edison Machine Works in 1884 before pursuing his own designs. In 1888, his work on the alternating current induction motor and polyphase power helped make rotating electrical machinery more practical. Tesla is often remembered through stories of solitary vision, but the historical achievement was more collaborative. Patents, machine design, transformer technology, manufacturing, finance, and engineering expertise had to meet before an electrical system could operate in the world. Alternating current offered an important advantage. With transformers, engineers could raise voltage for more economical transmission over longer distances, then lower it near homes, workshops, and street lamps. That did not eliminate losses, danger, or technical difficulty. It made new designs possible. Electrical networks still required expensive copper, careful insulation, skilled installation, standards, and constant maintenance. The important shift was not magic at a distance. It was the ability to treat generation, transmission, transformation, and use as connected parts of a single technical system. The struggle between competing electrical systems became known as the War of Currents. It was a conflict of patents, business strategies, public demonstrations, municipal choices, engineering arguments, and competing claims about safety. Edison interests took part in campaigns that portrayed alternating current as especially dangerous, including public animal electrocutions. The controversy became entangled with the first execution by electric chair, that of William Kemmler in 1890. But the episode should not be reduced to a morality play with one inventor as hero and another as villain. Electrical systems carried real risks. What mattered was how safety, profit, publicity, and technical design became bound together. In 1893, Westinghouse's alternating current system illuminated the world's Columbian Exposition in Chicago. The White City became a powerful public demonstration of what a large AC installation could do. Visitors saw electric light as a civic spectacle, brilliant, orderly, and modern. Yet one fair did not settle every technical argument forever. Direct current continued to be used, and electrical systems continued to evolve. Chicago mattered because it displayed infrastructure as an experience. The network became visible, not merely wires and machines, but a public promise that energy could be coordinated at a scale large enough to transform the built world. Niagara Falls made the scale of the new systems even clearer. The project was gradual. In 1895, the first Niagara station supplied power to local industry. In 1896, a long-distance hydroelectric transmission line sent power to Buffalo, more than 20 miles away. The point was not that distance had been permanently defeated. It was that engineers had demonstrated a new way to join water, turbines, generators, transformers, transmission lines, and cities into one coordinated arrangement. Niagara's power was not a free force escaping nature. It was water redirected through tunnels, machines, contracts, labor, and institutions. It is tempting to call such a network the first global grid. It was not. Late 19th century electrical systems were regional and national, unevenly distributed and dependent on particular places. But they established habits of interconnection that later grids expanded. Standard voltages, shared equipment, long-distance transmission, dispatch, maintenance, and public expectations of reliable service. Electricity did not make the world uniformly connected. It made connection itself a central technical and political problem. Who owned the lines? Who paid? Which communities received power? Which landscapes were transformed to supply it? Electrical power was only one part of a changing information landscape. Telegraph systems had already carried electrical signals over long distances before large power grids spread. At the same time, modern governments and businesses faced growing piles of records, names, addresses, occupations, births, deaths, shipments, accounts. The challenge was not simply to move energy faster. It was to count, compare, and sort information at institutional scale. This is where a more direct bridge to the history of computing appears, not in a mystical current, but in cards, categories, and machines built for particular administrative problems. Herman Hollerith approached that problem in the 1880s. Working on census statistics, he devised a system of punched cards, a punch for recording selected data, a tabulator for counting it, and a sorter for arranging the cards. The system was used for the 1890 United States Census. It connected administrative categories with electro-mechanical operation. A card represented data. An electrical contact registered a whole. Counters accumulated results, and sorting created new groupings. Hollerith did not create total knowledge. He built a practical answer to a specific problem of enumeration. But the principle mattered. Institutions could now ask questions of populations through formatted records and machines. A later philosopher, Martin Heidegger, called one tendency of modern technology Gestell, often translated as enframing. He did not write about Menlo Park, Tesla's motor, or Hollerith's census system as examples in the way we see them now. But his idea offers a useful later question. When a system turns water into power, people into records, or land into a resource map, what becomes easier to order and what becomes harder to notice? Enframing is not an accusation against every tool. It is a warning against mistaking what can be measured, stored, and extracted for the whole of reality. Modern data centers depend on reliable electrical power. Their servers, cooling systems, storage devices, and networks require grids that can deliver energy at scale. In that limited but important sense, The history of electrification is part of the infrastructure history of computing. But it is not the whole story. Electronic components, semiconductor physics, programming, communication protocols, corporate institutions, labor, extraction, and public policy all shape the systems we use now. The responsible question is not, did Tesla invent AI? It is, what systems of power and coordination make our digital systems possible, and who bears their costs?
Electrification changed how power could travel. Tabulation changed how institutions could count. Together, they helped make the modern world more coordinated and more dependent on systems that most people do not see. The next chapter turns inward. While engineers learned to connect generators, wires, cards, and counters, another tradition tried to model the hidden operations of the human mind. Sigmund Freud called this an apparatus of another kind. Not a computer, not a machine to be taken literally, but an attempt to describe forces beneath consciousness. The wires now reach the city. The next question is, what happens when the system reaches inside us?